What would happen if every glacier ice sheet and frozen mile of Earth melted at once? Most people imagine a single outcome, a global flood that wipes out our cities and ends human civilization. But the real consequence is far more radical. A full cryosphere collapse forces the planet into a new configuration. 24 quadrillion tons of redistributed mass distort gravity, slow Earth's rotation, lift the continents, and invert ocean chemistry. This is not merely a threat to humanity, it is a structural reboot of the planet. Human civilization evolved under one stable planetary configuration. This simulation examines what happens when that configuration is erased. And the first detectable shift doesn't appear at the coasts. It appears in Earth's gravitational field, the earliest signal of a planet abandoning its old equilibrium. To understand the true scale of this event, we must look beyond the shoreline. In a standard disaster model, the melting of Antarctica is treated simply as a volume problem at water-drowned cities. But this diagnostic reveals a far more complex reality. The cryosphere is not merely frozen water, it is a structural component of the Earth's engine. It acts as a gravitational anchor, a rotational stabilizer, and a global thermal regulator. When we delete this component from the simulation, the entire planetary operating system is forced to recalibrate. We are tracking a four-stage cascade failure. First, the redistribution of mass warps, the geoid altering the very definition of sea level and bending the ocean surface itself. Second, this mass shift applies a braking force to the planet's spin, fracturing our control over time. Third, the solid Earth, relieved of billions of tons of pressure, begins to uncoil like a compressed spring-shattering tectonic stability. And finally, the stagnant oceans undergo a chemical inversion, turning from a life support system into a toxic suffocant. This is a total systemic overhaul. Civilization is built on the assumption that the ground is solid, the sea is level, and the day is constant. This simulation removes all three certainties. The chain reaction begins not with water rushing onto land, but with water rushing away from the pole. The first warning light on our dashboard is the gravitational signature. The first anomaly is detected not in the water level, but in the attraction exerted by the ice itself. Standard disaster models rely on the bathtub effect, the assumption that when ice melts, the water rises uniformly across the globe like filling a tub. This diagnostic simulation proves that model false. We must understand the physics of self-gravitation. The Antarctic Ice Sheet is not merely a frozen reservoir, it is a gravitational titan, a mass of 24 quadrillion tons sitting at the bottom of the world. This immense mass exerts a measurable gravitational pull on the surrounding Southern Ocean, physically holding the water up against the continent's edge, much like the moon pulls the tides. When we delete the ice from the simulation, we also delete this gravitational anchor. The result is a paradox. While the global ocean volume increases, the sea level within a 2,000-kilometer radius of Antarctica actually falls. The water, no longer held in place by the ice's gravity, relaxes and flows away. The coastline of the continent does not drown immediately. It emerges. However, this local reprieve comes at a devastating global cost. That displaced water has to go somewhere, and the laws of physics dictate a violent migration north. As the ice's gravitational hold releases, the water migrates. We are tracking a massive vector of fluid motion, a global mass redistribution. The water liberated from the South Pole, combined with the melt from Greenland, does not settle evenly. Driven by the Earth's rotation and the relaxation of the gravity field, it surges toward the path of least resistance, the equator. Satellite telemetry tracks this shift as a gravitational signature. The simulation shows a catastrophic amplification in the tropics. While the global average sea level rise is projected at 70 meters, the equatorial regions experience a rise significantly higher due to this gravitational sloshing. The Maldives, the Amazon Delta, and the Indonesian archipelago are not just flooded. They are subjected to a hydraulic siege. The ocean is not simply rising, it is bulging at the planet's waistline. This is no longer a geography problem, it is a geodetic deformation. The mass of the planet is physically moving from the axis to the periphery. This redistribution physically alters the shape of the planet's gravity field, the geoid. The Earth is losing its oblate spheroid stability and becoming more pronounced at the middle. This warping of the gravitational potential surface has consequences that defy standard topographic maps. It forces water into continental interiors not just through rising levels, but by altering the level surface itself. In the simulation, we observe the Caspian Sea and the Black Sea. Separated for 5.5 million years, they are forced to merge. The rising ocean breaches the Bosporus, but the geoid warping also tilts the continental basin, effectively pouring the Mediterranean into the Asian steppe. Kazakhstan and Uzbekistan, previously landlocked, now face a new violent coastline. The map of Eurasia is redrawn not by politics, but by the warping of the planet's gravitational equipotential. But shifting 10 to the 19th kilograms of mass does not just warp the shape of the Earth. It destabilizes the spin. The planet is now unbalanced, and the brakes are about to engage. By moving mass from the axis to the periphery, we trigger a fundamental conservation law. The second systemic failure occurs in the planet's kinetic energy. To understand this, we must look at the conservation of angular momentum. The Earth acts as a spinning system where the angular momentum is the product of its moment of inertia and its rotational velocity. In our simulation, the migration of 24 quadrillion tons of water from the polar regions, the axis of rotation to the equatorial bulge, the outer rim, drastically alters this equation. We are witnessing the ice skater effect on a planetary scale. Just as a figure skater extends their arms to slow their spin, the Earth, now bulging with water at its waistline, increases its resistance to rotational acceleration. The planet's moment of inertia spikes. To conserve angular momentum, the rotation speed must decrease. The Earth strikes the brakes. It is the planetary equivalent of slamming the brakes at highway speed, except the vehicle is an entire world. This is not a subtle adjustment. It is a violent mechanical deceleration. The crust and the liquid core, which rotate at slightly different rates, are forced into a new alignment, transmitting torsional stress through the mantle. The planet is not simply getting wetter. It is undergoing a mechanical adjustment against the inertia of space. A deceleration in rotation translates immediately to a deviation in time. In the diagnostic simulation, we observe a temporal drift. The length of day, or LOD, does not remain constant. While a shift of a few milliseconds might appear negligible to human perception, it is catastrophic for the precision infrastructure that governs modern civilization. Our technological society is synchronized by atomic clocks that demand absolute stability. As the Earth breaks the correlation between universal coordinated time, known as UTC, and the planet's actual rotation, known as UT1, collapses, we observe immediate desynchronization in the global positioning system. GPS satellites orbit in a fixed reference frame, but the ground stations they communicate with are rotating beneath them. If the Earth slows down unexpectedly, the timing signals, which travel at the speed of light, arrive late. A timing error of mere nanoseconds translates to position errors of meters. In the simulation, automated navigation systems fail. Commercial aircraft drift off their predicted flight paths by dozens of meters. Autonomous cars lose synchronization. For the first time in decades, human operators are forced to take manual control of machines that no longer trust their own clocks. Power grids, which rely on phase synchronization frequencies tied to the rotation, begin to trip. High-frequency trading algorithms drift into chaos. We have effectively introduced a random variable into the fundamental constant of timekeeping. The planet is not just slowing, it is unbalancing. The redistribution of mass is asymmetrical. Antarctica is not a perfect circle, and the meltwater does not distribute perfectly evenly. This creates a wobble in the planet's rotation, amplifying the Chandler wobble to extreme variance. We are entering a phase of true polar wander. The physical axis of the Earth, the geographic north and south poles, must shift to align with the new principal moment of inertia. The solid Earth physically tilts relative to its spin axis to maintain equilibrium. In our simulation, the geographic poles begin to drift by tens of meters, creating a roaming axis. For an observer on the ground, the consequences are disorienting. The stars in the night sky shift their apparent positions. The celestial navigation maps used for millennia become obsolete. The Earth is hunting for a new stable spin state, wobbling like a dying top. As the planet wobbles and breaks, the solid ground beneath our feet begins to react to the changing stress. The lithosphere is not a rigid shell. It is stressed loaded and waiting to snap. The lithosphere is not rigid. It acts as a viscous fluid over deep time. To understand the third systemic failure, we must abandon the concept of the Earth as a static rock. In this diagnostic simulation, the planet behaves according to the laws of viscoelasticity. The mantle beneath the crust is not liquid magma, but solid rock that flows like extremely thick honey or pitch over geological timescales with a viscosity of approximately 10 to the 21st Pascal seconds. For millions of years, the Antarctic and Greenland ice sheets have acted as immense static loads pressing down on the crust with a force of billions of gigatons. This weight has physically depressed the continental bedrock, pushing it kilometers into the mantle, much like a heavy weight, sinking into a memory foam surface. The crust is currently in a state of high compression, storing vast amounts of elastic potential energy. When we delete the ice in our simulation, we trigger a massive stress relaxation event. The clamp holding the continent down is removed. The underlying mantle, which is under immense pressure, immediately begins to flow back into the space previously occupied by the depressed crust. This is not a simple mechanical springback. It is a complex fluid dynamic process involving the flow of semi-solid rock in the asthenosphere. The planet is trying to return to isostatic equilibrium, but the sheer speed of the unloading in our simulation creates a shock to the lithospheric stress field. The ground is no longer a stable platform. It is a dynamic surface in motion. This relaxation manifests as vertical velocity. We are observing glacial isostatic adjustment, accelerating from a geological creep to a visible upheaval. In the real world, this process is visible in Scandinavia, where the land is still rising at a rate of centimeters per year from the melting of the last ice age. In our accelerated diagnostic, this uplift becomes violent. As the weight of the ice vanishes, Antarctica and Greenland begin to rise, a process known as post-glacial rebound. The bedrock no longer suppresses surges upward. This has a paradoxical effect on sea levels. While the global ocean rises due to the added meltwater, the local sea level relative to the Antarctic coast might appear to fall or rise less drastically, because the continent itself is lifting out of the ocean. However, the mechanics of GIA include a dangerous counter-reaction known as forebulge collapse. When the ice pressed the continent down, it squeezed the mantle outward, causing the peripheral lands, the forebulge, to rise slightly. Now, as the center rebounds, that mantle flows back inward, causing the peripheral areas to sink. This means that coastlines far from the ice sheets, potentially in Europe or North America, might sink faster than the water rises, exacerbating the flooding. Entire neighborhoods could find the ocean rising from both directions, from above and from the sinking land below their feet. We are witnessing the reshaping of the ocean basins themselves. The container holding the water is morphing in real time. Rapid uplift exerts shear stress on ancient fault lines. The crustal deformation is not uniform. The rapid change in vertical velocity creates differential stress across tectonic plates, leading to intraplate seismicity. Fault lines that have been dormant for millions of years, clamped shut by the weight of the ice, are suddenly unclamped. The diagnostic detects a spike in seismic activity across the Antarctic plate and the surrounding oceanic ridges. But the most volatile reaction occurs in the West Antarctic Rift System. This region is home to a large number of volcanoes buried beneath the ice. Under normal conditions, the immense pressure of the ice sheet keeps the magma chambers stable and suppresses eruption activity. In the simulation, the removal of the ice load triggers decompression melting. As the lithostatic pressure drops, the melting point of the mantle rock decreases, allowing magma to form and expand rapidly. The volcanoes, effectively uncorked, enter a phase of synchronized eruption. This adds a new variable to our system: geothermal heat flux. The very ground that was once frozen is now heating from below, accelerating the destabilization of any remaining permafrost and adding thermal energy to the already chaotic ocean system. The basin reshapes, fractures, and burns, but the most dangerous state shift occurs in the fluid filling it. The influx of fresh meltwater destroys the density gradients that drive global circulation. The fourth and perhaps most lethal systemic failure occurs not in the rock or the sky, but within the fluid dynamics of the ocean itself. In a functioning Earth system, the ocean operates a global conveyor belt, the Thermohaline circulation. This vast engine is powered by the sinking of cold, salty, dense water at the poles, specifically the North Atlantic deep water, known as NADW, and the Antarctic bottom water, known as AABW. This sinking motion drives the ventilation of the deep ocean, pulling oxygen-rich surface water down to the abyss and cycling nutrients back to the surface. In our simulation, the rapid introduction of 24 times 10 to the 15th tons of fresh water acts as a thermal break. Fresh water is significantly less dense than salt water. When the ice sheets liquefy, they do not mix instantly with the surrounding ocean. Instead, they form a buoyant, low salinity layer that sits on top of the denser saline deep water. This phenomenon is known as hyperstratification. We observe the formation of a rigid pike-knock line, a sharp density boundary that acts as a physical lid on the ocean, because the surface water is no longer dense enough to sink the vertical mixing engine stalls. The Antarctic bottom water formation shuts down completely. The Atlantic meridional overturning circulation, known as AMOC, collapses. The global transport of heat stops, but more critically, the transport of oxygen to the deep ocean ceases. The lungs of the planet have stopped breathing. The ocean is now a stagnant pool separated into two isolated layers, a fresh sunlit surface and a dark saline abyss that is slowly suffocating. Without circulation, the deep ocean consumes its available oxygen reserve. The biological machinery of the ocean does not stop immediately. It continues to metabolize, and this persistence becomes the driver of the next phase. Marine organisms in the deep layers continue to respire, consuming dissolved oxygen, O2, at a steady rate. In a healthy system, this oxygen is replenished by the sinking currents. In our stratified simulation, there is no replenishment. We track the global curve of dissolved oxygen, known as DO. Within decades of the circulation shutdown, vast regions of the ocean fall below the hypoxic threshold of less than 2 milligrams per liter. We are witnessing the expansion of oxygen minimum zones, OMZs, from isolated pockets to a planetary scale. The first casualties are high metabolism organisms, apex predators, schooling fish, and cephalopods. They are forced into the shrinking surface layer or suffocate. As they die, their biomass sinks, feeding aerobic bacteria that consume even more oxygen to decompose the bodies, creating a positive feedback loop of deoxygenation. The chemistry of the water begins to change its electrical potential. The redox potential, known as EAH in the deep ocean, shifts from a positive oxidizing state to a negative reducing one. This is not merely a biological die-off. It marks a fundamental change in the chemical operating environment of the hydrosphere. The ocean is preparing to switch its metabolic pathway. When oxygen disappears, the microbial biosphere flips. Nature abhors a vacuum, even a chemical one. As the deep ocean becomes completely anoxic, with oxygen levels falling to 0 milligrams per liter, the evolutionary advantage shifts. Aerobic life, which depends on oxygen, loses ground to anaerobic life, which finds oxygen toxic. This marks a euxinic state shift. Dormant colonies of sulfate-reducing bacteria, long hidden in the sediments, suddenly find themselves in ideal conditions. They begin stripping oxygen atoms from sulfate, written chemically as SO42-, to metabolize organic matter. The byproduct of this process is not carbon dioxide but hydrogen sulfide, H2S. This is the chemical signature of a planetary poisoning event. Hydrogen sulfide is highly toxic to multicellular life. It is the same gas that once wiped out nearly all marine life during Earth's worst extinction. In the simulation, as the concentration of H2S rises, it begins to diffuse upward. The water column undergoes a terrifying visual transformation. Blooms of green and purple sulfur bacteria, microbes that thrive on light and sulfide, colonize the photic zone. The blue ocean turns a viscous, opaque pink. Fishing fleets vanish from satellite AIS networks. Coastal residents report the smell first sharp, metallic, almost electric, before the gas monitors begin to trigger alarms along the shoreline. This is a recreation of the Canfield Ocean conditions, or the chemistry of the Permian-Triassic extinction event, where 96% of marine species were liquidated. But the danger does not stay in the water. As the gas saturation reaches critical pressure, the ocean begins to outgas. Bubbles of hydrogen sulfide break the surface, entering the atmosphere. The euxinic gas is heavier than air and tends to pool near the surface, toxic to mammals at concentrations as low as a few hundred parts per million. The collapse of the ice has not just flooded the continents, it has converted the atmosphere into a chemical hazard zone. The oceans have reverted to a primordial state hostile to the civilization that mapped them. The cascade eventually finds a new stability point. In our diagnostic simulation, the chaotic transition phase defined by gravitational warping, rotational braking, and chemical toxicity does not last forever. Systems seek equilibrium. After the state shift is complete, the Earth settles into a new stable operating mode. We observe a planet that resembles the Eocene epoch of 50 million years ago. The sea levels have stabilized at 70 meters above the pre-industrial baseline. The atmosphere is thick, humid, and rich in carbon, maintaining a global average temperature significantly higher than the Holocene norm. The poles are no longer white, but green. Antarctica and Greenland are colonized by fern forests and temperate biomes. The rotation has locked into a slightly slower frequency, and the magnetic field has realigned with the new axis of inertia. This hothouse Earth is not a dead world. It is simply a different one. Life has adapted as it always does. The marine biosphere has reorganized around the new chemistry favoring organisms that can tolerate lower oxygen and higher acidity. The planet has successfully rebooted. The simulation confirms that the cryosphere was not a permanent feature of the Earth, but a temporary anomaly of the last few million years. The system has corrected itself to its historical mean, but this state is not new. It is merely forgotten. As the simulation concludes, we are left with one final haunting visual: the bare exposed bedrock of the Antarctic continent. For the first time in 34 million years, the land is visible. This unveils the ultimate variable in our diagnostic. Underneath the ice, we are searching for a specific signature. This is the Silurian reflection. If we scan this newly exposed continent and find nothing but rock and fossils, it confirms that we are the first industrial civilization to face this filter. But if we find traces, isotopic anomalies, refined metals, or geometric structures, it would prove that the system reboot is a cyclical process. The melting of the ice is not an end, but a reveal. It strips away the silence of the aeons to show us the true face of the planet we live on. The Earth is a self-correcting system. It does not care if the dominant species is reptilian, mammalian, or industrial. It obeys only the laws of physics. The ice will melt, the gravity will shift, and the chemistry will invert. The system will survive the reboot. The only open question in the simulation is whether we will.